Hey guys, this is Dan from Supernova, and today we're going to be looking at an important computer science topic known as logic gates. We're going to start out with a quick history lesson. So, computers evolved from electromechanical devices that relied on gears and mechanisms to do calculations. You can see pictures of those on the left there, and those eventually evolved into electronic computers that can turn the flow of electricity on or off. We can do this with tiny switches called transistors that are activated by the electronic signal that it receives. So there are two states to these signals, and they are one for on, meaning electricity is passing through the switch, or zero for off, meaning no electricity is passing through the switch. And we usually represent these as true or false, true being 1, false being 0. With just these two states, we can now represent most information in the form of binary. And also, conveniently, there's an entire field of mathematics dedicated to working exclusively with true or false values. This field of mathematics is called Boolean algebra. So in regular algebra, we use numbers and letters along with mathematical operations to be performed on those numbers and letters. In Boolean algebra, the only values we're using are true and false. And instead of mathematical operations, we're using logical operations. And you'll see what I mean in just a second. So the three fundamental operations of Boolean algebra are not, and or. And those can be combined to achieve different logical operations, which you will see in a sec. So the first logical operator we use is called not. And basically this not logic gate takes a single Boolean value, true or false, and negates it to the opposite. So example, if the input of the not logic gate is true, the output will be false, meaning if the gate receives a signal, it won't output a signal. If the gate does not receive a signal, it will output a signal. Next we've got the AND logic operator, logic gate, which takes in two values this time as input, and both values must be true for the output value to be true. So as you can see, if input A is false and input B is false, the output is false. And it is false for all the other combinations except for when input A is true and input B is true. And the final basic operator we use is an OR logic gate. And this one also takes in two values as input, and one or both values need to be true for the output to be true. That's why it's called an OR value. So A can be true for the output to be true, or B can be true for the output to be true. If both are false, the output is false. If both are true, the output is true. So it only needs one or both to be true for the output to be true. Now we can start combining these logical operators, and our first example of a combination is a NAND logic gate. So this one is the combination of a NOT and an AND gate, so the output is always true unless both inputs are true. So it's basically the exact reverse of an AND. Moving on, we've got the NOR gate, which is a combination of the NOT and OR gate. Both inputs must be false for the output to be true. So if any of the inputs are true, the output will be false. As you can see in that table, when both are false, the output is true. Any other time, the output is false. And the last combination we're going to look at is called an XOR gate, which stands for exclusive OR. And what this means is that the output will only be true if only one input is true. If both are true, the output is false. If both are false, the output is false. At least one has to be true, and they can't both be true. So these little logic gates might not seem that useful, but as you can see here, when we combine a lot of them, we can get a lot of crazy things done. In fact, this right here is called a 3-bit multiplication, and it is a combination of NOT and OR gates used to multiply two 3-bit numbers. As you can see at the top, it says A123, and B123, those are the bits of two 3-bit numbers. And now we'll head into Minecraft with the live segment of this webinar. And here we are in Minecraft. 2 secs, I just gotta get my instructions up for myself. So, we are in Minecraft. Just gonna open up the chat so I can see it. Okay. So we are in Minecraft. And the first thing I want to clarify is that with switches in Minecraft, up equals off or false, and down equals true or on. It's really confusing. I would have thought that up would have been on and down would have been off, but I guess that's not how Minecraft sees it. So going forward, up means off and down means on. So the first simple gate we're looking at is a very simple, straightforward. This isn't a logic gate. This is just if you give it input, you get the output. So if input is true, output is true. We don't have a name for this. This is just a simple transistor. Next one we're going to look at right now, and this one, the redstone torch at the end, redstone on, or actually we don't have to put redstone on top. You see, so now the lever is off and the light is on. It's a NOT gate. So when we turn this on, this turns off. Input is false, or sorry, input is true, output is false. Input is false, output is true. Simple NOT gate. So then the next one is an AND gate. You can see that sign says AND right there. Build a little contraption here. Switch here, switch there. Some redstone on top. We need some redstone. Another redstone torch. Finally a lamp. So you can see it kind of gets more and more complicated going down these logic gates. You can see that both are off, the light is off. So both are false, output is false. One on, one input is true, still the output is false. Two, the other input is true, the output is still false. But when we put both on, the output is true. So when both inputs are true, the output is true. It's an AND, because this one has to be on and this one has to be on. That's kind of the naming convention of it. Next, we're going to make the the OR logic gate. This one's pretty easy. Do it like this. We don't need these. So the OR one is pretty simple. This one can be on, or this one can be on. Both can be on. But if both are off, it's not on. So input can be, at least one input has to be on for an OR switch to output true. Okay, so that's the OR logic gate. And I just want to do a quick refresher to show how the table kind of adds with this. Just a sec.
So you can see that for the NOT switch, when the input is off, the output is on. You can see here with this, when the output is on, or when the output is off, the input is off, the output is on. When it's off, the output is off. Or sorry, when it's very confusing with the lever because of this whole thing, but okay. So we're going to move on to our this is one of the more complicated combination ones. So this one's the NAND switch. Lost. There we go. Two secs, sorry. I have a lot of screens open. It's getting confusing. Okay, so this is the NAND gate. And what this does, we'll see once we make it. So with a NAND gate, both have to be on, or sorry, neither can be on for this to be off. Oh, that is not in, sorry. Both levers have to be in the on position for this to be off. Any other way, the output will be true. If one is on and one is off, the output is true. If this one's on, this one's off, the output's true. If both are off, we get no output. That's a NAND gate. Next, we've got the NOR gate. And the NOR gate is cool. Put on this side, on this side. And it's very similar to the OR gate, except we put a redstone torch here. What we see happens is that when one is on, it turns off. When one is on, it turns off. If both are off, sorry, if both are on, it turns off. So one has to be on for it to be off. It'll be on no matter what, unless one of the levers is pulled. It's been very confusing talking about this with on and offs. And this one is the most complicated one. That's why it's the last one. This is the XOR gate. Got to put a sign up. So there's the XOR sign. Sorry about that. So the XOR one is very complicated. It's got two levers here. Torches here. Redstone. Redstone. Right. We got this here. And in the middle, got the light. So the XOR, what does that do? So the light, the output is always true when one of them is on. the caveat there is that only one of them can be on. It's an exclusive on switch. Oh, that worked. I forgot about these. There we go. So it's an exclusive OR. So only one of them can be on for it to work. When they're both turned on, it turns off. Exclusive OR logic gate. So that's the gates. And you might not be able to see the usefulness of this, but I added a couple of examples of how we might want to use these. So this is a reasonable example of an AND gate and a practical use of it. So when I open the door here, you see that this switch works perfectly. We can open and close the door. Over here, we have what I call a security switch. So when this security switch is on when it's on, this button won't work. It's a security door. Both switches need to be on for the door to work. So that's a practical example of an AND gate. The other example